Hello, let's look at free variables and parametric form. This is a definition we're going to use a lot. Free variables are going to come up a lot in the class. So let's read this. If the row echelon form of the augmented matrix for a consistent system does not contain a pivot in the column associated with a certain variable, then that variable is called a free variable. And in that case, we're going to write the solution in parametric form, which we already did once in a video from the other day, but we're going to get more into the details of it here. So this example here, it's not written as an augmented matrix yet, but we can go ahead and write this as an augmented matrix. And by the way, sometimes, I don't know if you noticed this, sometimes I use square brackets for matrices, sometimes I use round parentheses. It doesn't matter. They mean the same thing. So this is going to be 1, for equation 1 here is 1, 0, x2, 3, x3, and then a 2 on the other side, and a 0, x1 plus 1, x2, and then negative 1, x3, and then a 4 on the other side. And actually, this is already in reduced echelon form, reduced row echelon form, because the pivot positions are here. Those are the leading entries, and they're each a 1, and they're also the only non-zero entry in their columns. So we've got that. So according to this definition, let's see, first of all, is this a consistent system? Yes, this is consistent. And we can tell because the rightmost column, the last column, is not a pivot column, which means there's no row that represents an equation of the form like 0 plus 0 plus 0 equals 4. So that means it's consistent. There do exist some solutions. And so now let's look at the definition again. This is the row echelon form of the augmented matrix for a consistent system, and it does not contain a pivot in the column associated with this variable, x3. So that means x3 is a free variable. And when x3 is free, that means that this is actually ready for us to write the parametric form of the solution set. And to do that, we're just going to solve for each of the other variables in terms of the free variable. So that would look like x1 equals 2 minus 3x3, just subtracting that 3x3 from both sides of that, and x2 equals 4 plus x3. And you could just write down what x3 is, just to show that it's clear that that's another variable, and just write x3 equals free. But the actual parametric form means we're writing the solution set where we have a formula for the x1 and the x2 written in terms of x3, and we write that in the form of the points we're talking about. So instead of writing x1, we're just going to replace that with 2 minus 3x3, 4 plus x3 here, and just x3 for itself. And if you wanted to call x3 some other variable like t or w or something, that's fine too. So this is parametric form. There's also a few other ways you could write this that I think you could still call basically parametric form. You could write it like this. This is set builder notation, where we're saying the set of points of this form where x3 is any real number. And it doesn't really matter if you call it x3 or, like I was saying, any other variable like z or t or w or whatever you want. You're still talking about the same set of points. Now, let's look at what it looks like when we actually have to row reduce it first. Here's a couple problems you might be able to do yourself, but you never know until you try. You don't have to though, but if you have the time and motivation, you'll get more out of it if you do. So anyways, we're going to solve and write the solution set in parametric form. So let's start by rewriting it as a matrix so that we can use this information about pivot positions and stuff. So the first equation is 0x1 plus 1x2 minus 6x3 and then equals 5. The next one is a 1, negative 2, 7, negative 6. So here's the matrix we're talking about. Right now it's not exactly in echelon form because the staircase is going backwards. So we could just do a basic swapping operation. To get that into basic echelon form. And oh wait, but now it's not in reduced row echelon form because of this negative 2. So we do have, following the algorithm, we did get a 1 in the upper left corner here. And everything below that is a 0. So this pivot is already taken care of. Now we've got this 1 here is now the next leading one we have to take care of, and we want to make that be the only one in its column. So we just have to do a row replacement operation. We're going to do 2 times row 2 plus row 1 to replace row 1. That's going to be leaving row 2 alone. So we're going to get 1 plus 2 times 0 is 1. Negative 2 plus 2 times 1 is 0. What's the whole point of that? And 7 plus 2 times negative 6 gives you negative 5. Negative 6 plus 2 times 5 is positive 4. Alright, so now this is in reduced row echelon form. So this would be a good time to rewrite it as a sequence of equations using the regular old notation. And if you just solve this for x3 by adding the 5x3 to both, solve the first one for x1, I meant to say, by adding 5x3 to both sides, and solve the second one for x2 by adding the 6x3 to both sides, then it will look like this, and x3 is your free variable. And you can then write the solution set as this. Now, I just want to point out that if you erroneously forgot to get this in completely reduced row echelon form and just left it in row echelon form like this, you could still write this as a sequence of equations, or a system of equations. It would look the same as this one. It would just be written in a slightly different order. And you might say, well, we still have a 1x1 and just 1 times x2 in both of these equations, so you can still solve it for x1 and x2 and just add everything else to the other side. And sure, you could do that, and you'll get this. But the problem with this is it looks like there's 2 different variables you could plug in for x1. So you can plug in, you can take any value of x3 that you want. You'd have to plug it into the second formula to get x2 first, and then plug that into the first formula here to get x1 based on x2 and x3. So it's not really like directly solved for x1 and x2 in terms of just one variable like we want. So that's not really done. Not really what we mean by parametric form. Okay, so for the second one here, you can start by writing the system as a matrix. And following the algorithm, we already have a 1 as the leftmost entry of the top row here. So we're going to use that to do row replacement operations to clear away the 4 and the 5 in this column. So that's going to require a negative 4 times row 1 plus row 2 to replace row 2. and -5 plus row 1 plus row 3 to replace row 3. This gives you this result, augmented matrix here. So we got everything underneath that pivot position all cleared out with zeros. So now the rest of this is looking kind of suspicious. Maybe you know what's going to happen. The next thing we do is, if we're following the algorithm, is we're going to look at the second row and make the leftmost column have something non-zero in it, which is going to be that -3 right there. So we don't have to swap anything, it's already there. But then we can scale that to make that become a 1. So we're going to scale row 2 by multiplying it by -1/3. And then once we have that one scaled down so that we have a 1 here, that's now going to be our pivot position. I'm actually going to take that and use this row here combined with this row to make a new row 3. So I'm kind of skipping a few steps to save some space. Sometimes skipping steps is good because the more steps you show, the more things you have to write down, and sometimes just writing things down you make a mistake as you're copying something. So anyways, that's going to give you 0 plus 3 times 0 is 0. -3 plus 3 times 1 is 0, which was the point of that. And then, of course, 3 times 2 plus -6 is also 0. And then we're going to have -30 plus -20 is 10. Here I just wrote out what those row operations were that they just did. And now you can see where the pivot positions are. And lo and behold, one of the pivots is in the last column here. So this last equation actually says 0 equals 10, which is automatically false, which means because of that, the whole system really has no solution. There's no value of x, y, and z, or x1, x2, x3, whatever they're called, that will make this whole thing add up to 10. And that means the rest of these also have no solution. Anyways, it looks like you might say that x3 is a free variable because there's no pivot there. But we say that inconsistent systems don't have free variables, and there's no way to write a solution set in parametric form because there are just no solutions in it. So we can just write it as no solution. And you thought you were almost done with this video, but you got a little bit more work to do. Here's one to try yourself. Solve it and write the solution set in parametric form. And pause it here because the answer is going to show up in about 10 seconds. And here is that solution. So yeah, we find that y is actually a free variable here, and this last row ends up giving you just z equals 0. So we solve for x in terms of the free variable y and write it out as this parametric form, where everything's written out in terms of y. And I wanted to point out here that you could also use other parametrizations as well, meaning we solve this for x in terms of y, but there's no reason why we couldn't have just solved it for y in terms of x as well. And you can tell that, hopefully, that this equation here and this equation here is actually describing the same line. I just solved it for y instead. So when we say here, in the original one, x equals 2 minus 3y, we can basically say the same thing here by y equals 2/3 minus 1/3 x. And it's basically saying the same thing. So that's true with parametrizations of lines and curves and stuff in general. There's oftentimes a lot of different ways to do it. And That's okay.